Okay, what we're going to study now is work and kinetic energy. So, kinetic energy, what is it? Kinetic energy is the energy associated with motion. And so, what the energy has to do with is both how fast something is going and its mass. So kinetic energy is 1/2 mv squared. And what are the units of this? Well, the units are mass, which is kilograms, times meters squared per second squared, because it's velocity squared. And this is such an important unit that it's given its own name, which is a joule. So this is called a joule. Okay, so what would we do to change something's kinetic energy? Well, let's look at an equation that we've dealt with before. That's kinematic equation with constant acceleration. So if we were to multiply every one of those terms by half mass, we'd get 1/2 mass v final squared equals 1/2 mass v initial squared plus 1/2 mass times 2 acceleration times d. Well, if we simplify that a little bit, we know some of these terms. So the one on the left is just kinetic energy final equals kinetic energy initial. And if we cross off the 2's and we recognize that mass times acceleration is just force, what we're left off with is force times distance. Rearranging this equation, we get kinetic energy final minus kinetic energy initial equals Fd. Or in other words, the way that we change kinetic energy is by applying a force over some distance. Okay, so this idea of applying force over a distance, force over a distance, this is called doing work. So work is force times a distance. And when you apply a work, when you do work, it causes a change in kinetic energy. So work is force over a distance, and the units of work, well, since the change in kinetic energy equals work, these must have the same units. So the units of work must be joules. And we could show that by looking at the units of force times distance, and you'd get kilograms times meters squared per second squared. But if we think about this particular case where we've got some force going on, pulling on a block, the only force that really impacts the motion or the displacement is the force that's in the direction of the displacement, this F cos theta. And when we talk about force in the direction of the displacement times the displacement, so force in the direction of displacement times the displacement, well, that is an important vector scalar that we looked at earlier, which is that F dot displacement, that is work, because that equals force in the direction of my displacement times my displacement. And remember that this is a scalar. Okay, so I've already mentioned this, but we've got an important theorem which is we've already talked about, which is called the work kinetic energy theorem, which says that when you apply work, that equals the change in our kinetic energy. Or in other words, force times distance equals K energy final minus K energy initial. Notice, however, that we can only use this force times distance expression if we have a constant F. And we'll look in a little bit what happens when we don't have a constant F. So let's see how we can use this theorem. So imagine that we've got this crate and it is being displaced by a certain amount, and its displacement equals negative 3I. And there's a force going in the opposite direction, which is 2I minus 6J. The question is, if the mass of the crate is 4 kilograms and the initial velocity is 10 meters per second, find the final velocity. Well, we know that the work equals F dot displacement, which in this case is just negative 3 times 2, which is negative 6. So if there's negative work done on it, we expect that we're going to slow down the crate. Well, so that negative work equals equals Ke final minus Ke initial. Well, Ke initial was 1/2 mass times my initial velocity squared. Well, if I do some rearranging, I get 194 equals my kinetic energy final, which is 1/2 mass times final velocity squared. Looking for final velocity is going to equal, let's get rid of that squared, it's going to equal the square root of 2 times 194 all over the mass, which is 4. And we notice that this is going to be less than 10 meters per second. Okay, so let's think about the work that's done by gravity. Imagine if we have this book and we take one of these books and we're going to lift it up and we're going to put it on the table. And so we think about our final position there, whereas our initial position was on the ground. Well, if it started at rest and it ended at rest, we know that the change in velocity is 0, so the work done must also equal 0. But clearly work was done. Work was done by both me and by gravity. So the work done by me plus the work done by gravity must equal 0. Or the work done by me must be negative the work done by gravity. Well, what work is gravity doing? Well, gravity is pulling down with a force mg. And the book is going up, so it's in the opposite direction of the force. So the work done by me is negative the work done by gravity, where that is negative mg times h, where h is the height of the table, the distance it moves. So we could simplify that to saying the work done by me equals mgh. And we'll come back to this later, but this is a very important idea in terms of, even though the final velocities was 0 and the initial velocity was 0, work was done. It was just that two things were doing work, both me and gravity, and that resulted in a net work of 0. So let's think about what happens when you have a variable force. So let's imagine that you have a force only in the x direction. So let's say in the x direction. And your force is varying with position. And if we want to look from A to B about the work done, well, we know that work has to do with force over a distance. So if we were to look at, a little sliver right here over a little dx, that sliver represents a little bit of work. And so we're doing a little bit of work, which is my height of f times a little bit of x. And so if I wanted to find the total work, that would be the integral of all those little slivers, which would be the integral of f dx from A to B. And so now here we're going to start using calculus to find work when we have a variable force. Remember, this only is in the x direction. What happens if my force was in two directions? What if instead of 2 dimensions, or 1 dimension, or 2 dimensions, let's just go the biggest, which is what if we're talking about in 3 dimensions? So if we're in 3 dimensions and we're applying some force over some displacement, let's call my displacement, which is both in the x, y, and z directions, let's call my displacement r. So the work done would be the integral of f over a little bit of r, dotted from r initial to r final. But what we know about the dot product is we can then just split that up into their respective components. So work then is just going to be the integral from x initial to x final of fx times dx plus the integral of y initial times y final of fy dy plus the integral of z initial to z final of fz dz. And the important thing to remember is that this work done in 3 dimensions results in a scalar. So it's going to tell us something about the change in the velocity, but it won't really tell us what change, the change in which direction. And so that's it for now.